So my name is Vicky Hamilton. I'm a member of the OSIRIS-REx mission team. I am both a member of the science team and I lead what is called the Spectral Analysis Working Group. We're the group of scientists primarily interested in interpreting the results that come back from the spectrometers on the spacecraft. I'm also the deputy instrument scientist for one of the instruments on the spacecraft, which is called the OSIRIS-REx Thermal Emission Spectrometer. And you'll hear a little bit more about that in a moment. But I'll start out with an overview of what OSIRIS-REx means. Like all good missions, OSIRIS-REx is actually an acronym for many more words. We start with the O in OSIRIS, which stands for origins. So one of the primary motivations for this mission is to obtain a pristine sample of material from an asteroid that is called carbonaceous. So it has a lot of organic material on it. And the reason we want to understand that is because we do want to understand the origins of life in the solar system. Is life on Earth a unique thing? What are the building blocks of the chemistry for life? And that a lot of that lies in understanding organics. The organics we have in meteorites have all come through the Earth's atmosphere and landed on the Earth somewhere, so a lot of times they're contaminated. So we want to get a sample that's uncontaminated. The SI in OSIRIS is for spectral interpretation. We want to provide ground truth for the observations we've made from telescopes. And the way we do that is to actually go to the asteroid and measure it a lot closer where we can see it a lot better and use that information to help us better understand telescopic observations of other asteroids that we won't be able to go to. The RI in OSIRIS is resource identification. So there's been a lot of interest lately in what's called in situ resource utilization, both on the Moon and Mars, but also from asteroids, where there are organic materials, water, metals, things like that, that people are interested in potentially sort of mining, if you will, in situ or at that particular object. So we're going to provide information that will give people more insight into what resources are available, what form they're in, how hard they might be to get to, and so on. The S in OSIRIS is for security. So the target asteroid that OSIRIS-REx will go visit is a near-Earth object. It crosses the Earth's orbit in its own orbit, and it in fact poses a very small risk to the Earth that it might impact Earth sometime in the next couple hundred years. There's about a 1 in 1,000 chance of that happening. So there's a real question about, do we have to worry about this asteroid or others impacting the Earth and causing damage? So there's a property called the Yarkovsky effect, which basically is the influence of the sun on the orbits of small objects like asteroids. The sun actually exerts pressure on these small objects. It changes their orbit over time, which can either lead them to come closer to Earth or go farther away from the Earth. By measuring the temperature of the asteroid up close, we'll be able to get a much more precise measurement of this effect on this asteroid, and then that will help us understand its changing orbit and how the orbits of other asteroids can also change over time. And then the REx is Regolith Explorer. So one of the things that we like to do, regolith is just a fancy planetary science word for the ground. It's the part of the asteroid that's been impacted and is made up of dirt or soil. I shouldn't call it dirt or soil because that may imply plant material, but it's rocks and pebbles and dust and things like that. And so what we're going to have the opportunity to do with this mission is document that regolith, that ground surface, at very high resolution, much higher resolution than other missions, down to centimeter to sub-centimeter scales. So to look at the mission itself, we have this big long timeline. So the mission started in 2010. And the point of this slide is not to have you try to understand what all these different milestones are or know what they are or understand, you know, what the significance of each one is. The point here is to simply say there's an incredible amount of planning that goes into any mission, but especially a mission where you have to go to an object, characterize it, get a sample, bring that sample back. There's all the preliminary work you have to do to design the spacecraft and the instruments and make sure that it all will achieve what you need to achieve once you get to the asteroid. So our first milestone was that we were selected for flight in May of 2011. We've been through several reviews each year to make sure that we're on track to build the spacecraft and the instruments that we need to build in order to fly this mission successfully. Our most recent success was that the spacecraft was going through what we call ATLO testing, or assembly, test, and launch operations. And so all the instruments were delivered, the ATLO process has gone through, and the spacecraft has now been delivered to Kennedy Space Center to do the final preparations for launch, which will occur in September of this year, 2016. Once we get to launch, we don't go straight to BENNU. We actually go around the solar system once, come back towards the Earth to get a gravity assist that will fling us out to BENNU. That will happen in 2017, and then another year later after that, or about 2 years after launch, we arrive at BENNU in August of 2018. We do our operations at the asteroid for a couple of years, and then when we're done characterizing the asteroid and collecting our sample, we'll bring the spacecraft back to the Earth and depart the asteroid in 2021. We get back to the Earth in late 2023, and then the mission finally concludes after the sample analysis occurs. Once we've gotten it back, we want to have time to analyze it. So the end of the mission won't occur until that work is done in late September of 2025. So the whole point here is to say there's a whole lot of planning, there's a lot of different milestones, and we know very, very far out what we need to be doing and when. So there's a lot of organization that goes into this. If we look in a little more detail at the asteroid operations, this is the period only when we're actually at the asteroid. So again, the point is not to understand what all these different things are, but to simply understand that there are many different phases of our operation. We're a little bit unlike other missions in that regard. There are a lot of missions that will go to their target object and go into orbit and make similar observations over years to look for change and characterize objects. We have different kinds of mission phases where in one phase we'll be at one orbit, in another phase we'll be doing something else, and all of this leads up to characterizing the asteroid so that we can go into our rehearsal phase where we get down to a couple of sites that we're pretty sure we want to collect the sample from, and then we'll do our reconnaissance and make sure we understand what's at those sites. And then we'll start practicing for the sampling event. We don't want to just try it the first time. We want to make sure we know exactly how we're doing it. We have to operate this spacecraft very, very close to the surface of the asteroid, ultimately touching it. So we want to make sure we understand everything that's involved in that. So we're going to rehearse that process a couple of times before we actually collect the sample. And then once we have the sample on board successfully, we'll wait around the asteroid for a period of time just to get the orbital configuration correct so that we can then return back to the Earth and cruise back. But again, another sequence of events that are all very, very carefully planned out in advance so that we know what we need to be doing at each point in the mission. So a very important question is, what is the object we're going to and why did we pick it, right? So we're going to an asteroid called BENNU. It is an Earth-crossing asteroid, I've already mentioned that. So its distance to the sun is just right. We have about 500,000 asteroids that we know of or estimate to be present in our solar system. So the question becomes, well, how do you pick one out of that many asteroids? And so the diagram on the right sort of shows the progressive sequence of criteria that we applied. So we start with, 500,000 asteroids. But of those, we're only interested in the ones that actually come near the Earth. So those are the near-Earth objects. There's only about 7,000 of those, plus or minus. That's still a big number to choose from. So then we come back to, well, okay, which ones are going to be in the best place for us to go and come back? Because we have to be able to do both parts of that. So when you constrain that, now you get down to just under 200 asteroids that are really optimal for going and coming back. Then you want to get an object, an asteroid, that's big enough that it rotates slowly enough that it hasn't flung away all of its pebbles and dust and all of the stuff you want to collect. Because it turns out that very small asteroids rotate very, very quickly, and we think all of those small particles are gone. So we needed an object that was bigger than 200 meters. So that gets you down to 26 asteroids. It's starting to get to be a problem you can solve, but it's still not ideal. That's still a lot to choose from. So then we get to our origins question, this idea of organics that we want to sample from a pristine environment. By the time you get to that requirement, now you're down to only 5 asteroids, and it becomes much easier to choose one. And so we came to, at that point, to selecting BENNU. So that's the story of how we got to BENNU. So BENNU, this is some of the best imaging that we have of BENNU so far. The image on the left that's kind of looking a little like noise that's kind of sparkling over there is actually an animation of radar imagery. And so that's showing us something about the shape and roughness of the object. And from these radar data, what we can do is construct what we call a shape model. And that's what you're seeing on the right. The right is an animated version of the shape model that shows us what BENNU is shaped like and how it rotates so that we can start making plans for how we're going to operate around this object. So BENNU is about 500 meters in diameter, so it's a really rather small object, half a kilometer. It is roughly spheroidal, sort of like a top. Makes it very different than some asteroids people might be familiar with, like Eros, which is shaped kind of like a big potato. And its rotation rate is about 4.3 hours. So a day on BENNU is only 4.3 Earth hours. So it's rotating reasonably quickly. We also know a little bit about its bulk density. It's a little under 2 grams per cubic centimeter. For reference, the Earth is much higher, around 3.2 to 3.5 on average, and that's because we have a lot of very dense rock. These asteroids are a lot more porous, a lot less dense, so they might be constructed with ice in their centers. They might just be very porous, but that's part of what we're going to go try to figure out. So how will we actually learn about BENNU? We have a suite of instruments on the spacecraft that are all designed to do the characterization that we really want to do. So the first instrument I'll talk about is OCAMS, or the OSIRIS-REx camera suite. It's actually 3 cameras, one for imaging our sampling site at very, very high resolution. The next one is called the MAP camera. It's the one that's going to help us characterize the asteroid before we do the sampling at high resolution. It will also help us do some of our navigation activities. And then we have the polycam, which is basically almost, you can think of it as a telescope. It's the camera that will allow us to see BENNU while we're still out on the way to BENNU. It's going to be the camera that first spots BENNU as we're on approach. So those cameras will give us all of our visual, photographic characterization of BENNU at multiple scales. OLA, or the OSIRIS-REx laser altimeter, is an instrument provided by the Canadian Space Agency that's going to give us topographic information in great detail about the surface so that we have a much better model of the shape so that we can be very, very careful when we're picking our landing site, or sorry, our sampling site, it's not really a landing, and make sure that we won't run into any big boulders that we weren't aware of or anything like that. We'll have very, very detailed surface information from that instrument. The next 2 instruments are our spectrometers. One is a visible and infrared spectrometer provided by Goddard Space Flight Center, and then the other one is the thermal emission spectrometer. So both of these instruments will characterize the composition of BENNU, and then the thermal emission spectrometer, OTIS, will also measure the temperature information, where I was referring earlier to the Yarkovsky effect, and the amount of thermal energy and how that can change orbits over time. We'll get that information from OTIS. The University of Colorado at Boulder is in charge of a radio science experiment that will help us understand the mass and gravity and geophysical properties of the object. And then a bunch of very, very bright students at MIT have built an instrument called REXIS, which will measure the elemental abundance of the materials on the surface. So that's our suite. And so to start wrapping up, what I wanted to close with are some of the key things that OSIRIS-REx will do that are of even more broad importance than the specific goals of this particular mission at this particular object. We're learning a lot about how we use astronomical data, telescopic data, things like that, to characterize faraway objects before we've had a chance to visit them, and to help us understand what we need to be able to do when we get to them and what we need to be prepared for. So we'll be able to use all this, we're using astronomical information to help us prepare the mission, but once we have the mission data, we'll be able to go back and say, how well did we do? And how does that influence what we think we know about other objects that we haven't visited? We will do that through measuring global characteristics of an asteroid with a new suite of instruments that hasn't been flown before, so that'll be a new view of an asteroid. And especially with the instruments that we have this detailed characterization that nobody's ever done at these scales before, where we're looking at things, you know, just very, very small scales of an entire asteroid. That'll tell us a lot about asteroids in the solar system and the things that happen to them over time. Another thing that's really different about this mission relative to most missions at asteroids is that we have to operate at the asteroid on a timeline that's unlike a lot of missions, where a lot of missions can go to an object and they can go into an orbit and make a lot of observations, and there's time to analyze those data and think about them. We have a very short timeline. We have to measure properties about the asteroid, understand what it's telling us, and then make decisions about where do we want to go and sample. And we can't just take all the time in the world to do that. So we call that a tactical timeline. And the best analogy for that elsewhere in planetary science is Mars rovers. Mars rovers operate on that same kind of timeline, where you get the data back that you took yesterday and you have to interpret it very quickly to decide where are you going to go or what are you going to do today. And we will be operating that way at an asteroid for the first time. We also will be demonstrating very accurate navigation in a microgravity environment. Most spacecraft don't do the kinds of operations where that we will do, where we're coming in close, looking, backing away, doing different kinds of observations, and then actually coming into contact briefly with the asteroid. So that's the next point about delivering to a specific location. We've got to not just pick a place, but we've got to actually go to it and be accurate as we do that. And then we have to successfully collect the sample, bring it, put it, stow it, get the spacecraft away from the asteroid so that we don't damage it, and then return the sample safely to Earth. So there's a whole lot of things that will be new technologies and provide a great deal of new information for future missions. And so finally, I just wanted to wrap up by pointing out that we have a very broad social media presence on Facebook and Twitter. We have a website. Our PI has a blog that he keeps where he talks about his experience on what's happening with the mission and particular activities that are going on. And then we also have a series of 321 science videos that explain a lot of the concepts around what we're doing with this mission, like things like the Yarkovsky effect and asteroids in general. So thank you very much.